So this is a little bit of a change of pace from the previous talks, which have been about, I guess, constructing and visualizing models. And what I'm going to show you is more about, I guess, the practicalities of running large models so I guess you might have some experience just from yesterday where Tom helped you make this model that you had to let run over lunch, right? It took like a half an hour. And so even models made of very simple rules can take reasonable amounts of time to run. And if you need to run a stochastic model thousands of times or hundreds of thousands of times to see rare-ish events, you might start wondering if there's a smarter way to go at the problem. And so there's a method of enhanced sampling called weighted ensemble sampling that had its start in I guess, the structural biology world in protein simulations, which are very computationally expensive. So people are very interested in speeding up simulations. And we've been applying this methodology to systems biology models. And as these models get more and more complex, I think it becomes more important to be able to simulate things in a reasonable amount of time. So this whole algorithm is based on a very simple idea of statistical resampling. So say you have an original sample from an underlying distribution. Here it's a 2D Gaussian, right? And so there's 500 samples. Maybe that's too much for you to store in memory or something, and you downsample it, right? That's a pretty commonly accepted, reasonable thing to do. So you lose some accuracy in your representation, but it's still statistically exact. Like if you did this over and over again, you would build up the exact histogram of the underlying distribution. You can also go the other way. And this one, which you could call upsampling, I guess, no one really does because it's not interpolating anything. It's just if you have 500 points, you can double your sample, like literally make another copy of the list of samples. And now you have 1,000 points, and each of them have a probabilistic weight of half of what they used to. You have no new information, but you could do it if you wanted to, right? You can also do this in homogeneous, like differentially in different spaces or whatever. You don't have to just upsample or downsample. You can do different resampling events in different parts of your sample space. And so that is what the weighted ensemble algorithm is built on. You use a stochastic process, that's your underlying distribution, and you resample iteratively as you step through time. And so it's just repeated resampling events where you upsample things where you care about events and downsample where you don't. It can be any underlying stochastic dynamics. Like I said, this got started with molecular dynamics. We worked on it with the cell signaling models in BioNetGen, and we've been applying it to M-cell models. And so the nice thing about this is that you maintain statistical exactness. You don't have to bias anything ever. So the algorithm is called weighted ensemble sampling. What is a normal ensemble sampling method? It's just basically running your stochastic system a bunch of times. So here I start out, I guess, 8 trajectories that all have a probability. They contribute to my probability mass with weight 1/8. And then I step through time. And at each time step, each trajectory has a different random seed, so they do slightly different things, right? And by the end of my simulation, after 3 time steps, I have this histogram of where things might be. That's my belief of what would happen. And so I do a bunch of repeated runs, and I can make this histogram. I normalize it, and it's a probability distribution. And so you can this is perfectly parallelizable, right? So you're not stuck just cranking these out on a single core, but you can do better than perfect parallelization. That's the point of this method. And so instead of just stepping through time with parallel trajectories, the weighted ensemble algorithm, you at each time point, or at some fixed time point, you do these resampling events, right? So I start with one trajectory, and I immediately just make a parallel copy of it. So now I have 2. I didn't even simulate any dynamics. I just made 2 trajectories. And then, so I step through time, and each one does something different because they have different random seeds. And then I resample again, and I split each trajectory. And so now these two trajectories share a history, but from now on, they're free to do different things. And then I step through dynamics again, and so one of them stays in this rarer region of space, and another one falls back down, and I say, well, I don't want to just keep splitting forever and ever. I'll get an exponential number of trajectories, and that doesn't really help me. So whenever there's too many things together, I'll downsample them. And so two of these come together, and whenever I don't have enough things, I'll upsample them. And so that's the process where you basically say, I want to spend a given amount of computational resource that I have looking at different parts of space. That's the gist of the algorithm. And it lets you, again, at the end of the day, you can make a histogram of what you believe your probability distribution is. And now the building blocks of your histogram have different sizes, right? So instead of trying to build a histogram that represents something with very skinny tails with these fat chunks of probability, I have much finer resolution where it's appropriate. And I'm not spending so much time sampling the peak, because if I run dynamics, just bunches and bunches of parallel trajectories, by definition, I'll sample the center of the distribution where the peak is, right? That's where most of the events happen. And I have to wait sort of exponentially long times to sample these rare events. Whereas if I apportion my sampling along the x-axis evenly, then I can sample these rare events and sort of decouple the probability of those events from the waiting time to seeing them. And so here's sort of one way to visualize this. So here's a double well potential, and I start out in the bottom well, and then I wait to see, if I transition over into the other well. And so the red stuff is the brute force approach, and there's like 100 or 1,000 simulations, and they all just sort of wander around and stay in the well. And then the blue lines are these branching weighted ensemble processes, and as you branch, you get less and less probable. And so these trajectories have a very low statistical weight, but they're able to sample sort of the range of possibilities more efficiently. So we applied this this past year or so to a neuromuscular junction model that Marcus was interested in previously, and so it's a model of one active zone, and there are these 26 vesicles here, and there's calcium diffusing around, and after the calcium is released, it can bind to these vesicles, and if enough calcium binds, then you have a firing event. The firing probability goes down as a power law pretty strongly as the calcium concentration decreases. So it's a sort of a fourth or fifth order relationship. So as you crank down the calcium concentration, it becomes very, very difficult to simulate these firing events. You have to run tens of thousands or hundreds of thousands of simulations. And so here we compared looking at the firing time distribution in this sort of low calcium regime using the same amount of computational power with the weighted ensemble approach and this sort of standard brute force approach. And so you see, when the events are sort of rare-ish, and these weren't particularly rare, but you get more resolution, you get to see the shape of this, and you get better confidence intervals in these measurements. The brute force, it's on a log scale, and the brute force approach couldn't exclude 0, so the error bars don't really make much sense. And so here's a plot of as you take down the calcium concentration, the probability goes down quite a bit. So here at the very low concentration, things were only firing once every 10,000 times or so. So you'd have to run a ton of these simulations in a naive manner to be able to validate this model in the low calcium regime. And then again, up here where things happen, 1 every 10 or 20 times, this method might not help you that much. So you know, it's not perfect for everything, but if things are hard to see, then it's fairly helpful. We also applied this to this model that I think you'll see more this afternoon. This compartmental model that's simulated in a realistic geometry, and it's sort of this transduction cascade, but the end result is transcribing and translating these couple of proteins. And this model takes quite a long time to run, you know, days or weeks to see good statistics for producing this protein. And so, again, here's a histogram of the likelihood of things happening, and it's on a log scale, and you can't actually see the two colors, but they're here because 99% of the time nothing happens. You don't get to produce any of this this second protein. It's the last thing in the cascade. After 400 seconds of simulated time, usually nothing happens. But if you allow this sort of branching process to encourage rarer and rarer things to happen, you can get an idea of how likely sort of reasonable numbers are to happen in a short time scale. And it turns out it's fairly unlikely for this to happen. It's, you know, 1 in 1,000 times you'll get five proteins in 400 seconds or whatever. And so you might say, well, okay, that's a quantified result, but why is that useful if it's so rare? And I think there's a couple answers to that. You know, rare events can matter. If you have, you know, trillions of cells, it only takes one rare event to start a cancer sort of kind of thing. But here, the more direct answer is that there's a really nice relationship that relates short time scales to long time scales if you're in a steady state. So okay, the little cartoon I showed before, there was this same potential, and it was chopped up into 3 bins. And here's time passing, and I've changed my setup where that if I start here and I end up here, as soon as I end up, I'm going to artificially pick up this little probability, this trajectory that has a probabilistic weight, and drop it back where it started, and try to set up a flow of probability from an initial state to a final state. So it's a sort of a weird thing to do, but you do it because there's a very simple relation that if you're in a steady state, if I measure the flow of probability into a target state per unit time, then I can estimate the mean first passage time to that event by taking the reciprocal. And so this can be a short time scale, and this can be a very long time scale. And it lets you estimate long time scales from short simulations. And so this is what we did here. We were measuring, using that other, this data here, where this is a short simulation with rare events in it, watching as things arrived into this target state and then letting them go back, and plotting, you know, when these things happened and how likely they were. We were able to estimate this first passage time to producing a critical number of proteins as, you know, 5,000-ish seconds, which is much farther beyond our capacity to simulate than is reasonable. So I guess the idea is that, yeah, if rare events are important, and often they are, even if you don't maybe think they are naively, this methodology can be helpful to you to simulate your system in a reasonable amount of time and to gather statistics about it. I think the other idea that's interesting is that you can get speedups that are large enough that you can maybe be encouraged to make more ambitious models. And the extrapolating long time scales from short simulations is also a nice benefit. So the code to do this is freely available. It's mirrored on GitHub, and there's also a workshop about using this methodology for sort of any stochastic simulation engine that you're interested in using this July. And there's more details at Lillian Chong's website if you're interested. It's also through the MMBIOS collaboration, so I think it should be on that webpage too. And so this is work that we did together with Marcus and Jim and Jose, and Devin, and they can tell you a little bit more about it if you're interested. But thanks. Any questions? Yeah.
If I imagine it in the limit, right, I would have a uniform distribution, and all the information would move to the weights of these events. They would be all equally likely, right? And so what then happens to the error that propagates to this multiplication or reduction of the of those probabilities, right? Because the error propagates throughout as I'm up to the point. If it's something rare, right? It multiply it, and so the error multiplies as well and propagates throughout. So what is the ultimate error distribution in this system?
So I'm not quite sure I understand the uniform distribution part of the question.
Well, you are making the rare events more likely by multiplying the particles that are in that state, right? So
yes.
And the events that happen often, those you are reducing.
Yes.
So ultimately, you are making them more equal, and the information about how often things happen go into the weight.
Yeah. Yes, that's absolutely right. Yeah. So the idea is that if you have a naive sampling where, I guess the idea being that when you make a histogram, the error bars are proportional to 1 over the square root of the number of samples that went into it. And so you're stuck in a naive approach. The error bars of the large bars are tinier, right? Even compared to their size, they're tinier. Whereas if you do it this way and you decouple the weights from the error estimation in terms of the number of samples that go into making this, now everyone's on an equal footing. So one way of thinking about it is that you sort of get to redraw the variance of the distribution to suit your needs. So if you really care about this space, you could say, well, I want to have 100 of these trajectories here because I want a really nice measurement here, and I only want 4 here or whatever. And you're right that the error does propagate through, but I think we've found that after a certain amount of mixing time, everything sort of shakes out and it recapitulates. So error does propagate, and there's definitely correlations. So these trajectories share the same history, right?
Yeah, exactly.
So you have to wait for a decorrelation time, which I guess you don't know what that is a priori, but you have to wait some time, and after that, then things are okay. So yes. Right. So yeah, this isn't a real potential, and usually you don't even know the potential ahead of time. But if you have a simulation, you can chop up the state space however you want. So I could say, well, this bin means that I have 2 proteins in my simulation, or this bin means that my molecule is now 2 angstroms away from being folded rather than 1 angstrom away from being folded. So you pick a coordinate or multiple coordinates along which you can chop up your space, and it can be as abstract or concrete as you want. But yeah, you pick some way to measure that's of interest to you, and then you chop up your state space like that.
So what is the reason
That you
I didn't get that top theory? So, I mean, how to decide to that you are going to go with half or 1/4 of the molecular
I mean, one thing I think she's asking, and we should make clear, you don't ever move a particle. You don't ever decide to move a particle from one bin to another. That happens. It has to happen from the simulation. If it doesn't happen, you have no method. There's there's no way to move a particle from bin 2 to bin 3.
So,
It only happens only through simulation for a
once
period of
it
time.
happens, then you divide.
Yeah, so if
Yes.
it happens, you can now, if a particle goes from one to another, you can now split it and sample many trajectories following, from being in bin 2. But you're also splitting the probability among those now, which is why the weights get smaller and smaller as you go to the right. But you still have to actually see the transitions happen in the system.
Right, so there's a little bit of an art to picking this time scale so that you see things interesting before they decohere or whatever. Yeah?
I'm curious, like, you can talk about, if we look at the simulation, like, what is the origin of the events that you see? So, like, if you see a low copy, like, I'm wondering if you see a low copy number, or if it just happens that the Ensemble algorithm is sampling and picking everything, like, weird genetic traits from the distribution. Like, I'm wondering if you know what the origin of your experiments are, or why it happens.
Right. It can be for almost any reason. I drew this picture to represent sort of this potential barrier that if you have to climb a hill and you just do it by randomly walking around, usually you're going to slide down that hill, but sometimes you'll ratchet your way up. And so, if you have an activated process or whatever in a structural problem, then crossing energy barriers is exponentially unlikely. So that's one origin. If you have a spatial simulation and you have to diffuse around, then diffusion can take a long time, and it'll be very, very unlikely that if you start up here, you're down here, in a short time. So that can be a rare process. You can also have processes where you switch between states in a chemical reaction network, and the copy number of one molecule represses the copy number of another. And so, you can make a molecule of the repressed species, but it's very rare that it'll stick around until another one gets made. And so, yeah, it doesn't particularly matter the origin of the rare process. I mean, of course, you need to know stuff about your simulation to divide up space intelligently, but it's fairly agnostic to the underlying dynamics, if that makes any sense.